By Joel Moore from Berkeley, and he will tell us about topological phases in condensed matter.
Thanks. I'd like to thank the organizers for the chance to speak here. It's fun to try to explain what one does to a slightly different audience. The field of topological phases is about 30 years old, but it's been sort of reinvigorated in the last few years, mostly by experiment, and it's thrown up a few hard problems where we in condensed matter could definitely use some help from high energy physics and particularly new methods like ADS, CFT. Unfortunately, the first lecture is not going to have any gravity in it, and it will be essentially a condensed matter lecture, and it won't even require that much interaction between the electrons. It does actually wind up depending very much on non-abelian gauge fields, though, in a funny way. So if you can stay awake till the end, I think you will start to recognize objects that you know and love after we get through the sort of simple review stuff. So these are the people who are involved in various stages of the work. I do have a set of lecture notes from a course I gave at Berkeley, and shorter versions are also available, which you can find there. If you're interested specifically in mathematical aspects like braid groups and so on, there's a very nice little book by Zhenghan Wang that I would recommend. Okay, so this is what I want to cover, and I'll be going back and forth between the slides and the board, I hope. So basically, topological order, we now realize, is quite common in nature. Just in the last 5 or 6 years, we found the first examples of fairly ordinary three-dimensional materials whose properties you have to understand in terms of topological order. So I'll give a couple of definitions of what that means as we go along. But basically now it's getting more mainstream in that it would be hard to justify doing a solid state course or something without explaining some of these ideas. It all grew out of the quantum Hall effect. So I'm going to start off by explaining the quantum Hall effect in a slightly unusual way, which generalizes very naturally to what are called topological insulators. And that's kind of the big recent discovery in this area of nearly non-interacting or phases that we can understand without interactions and are topological. And it turns out that somehow the one big story of the history of topological phases is that particle physicists invent something thinking it might be a quote-unquote fundamental theory of nature. It turns out that it isn't or might not be, but it winds up being realized in condensed matter. So that happened with Chern-Simons theory, famously in the quantum Hall effect. And more recently, it happens with something called axion electrodynamics that people like Wilczek and Sakivi were worried about. So that turns out to be the right sort of effective theory of topological insulators, and that's what I'm hoping to get to in this first lecture. Then we will talk a little bit about more complicated things as I move on. As far as why these topics were chosen, so it's hard to do justice to the full field of topological phases even in 3 lectures, I tried to choose things that reflect a nice interplay between condensed matter and other areas of physics, and also to be able to justify some open problems where we want things from new methods like the correspondence that you're all experts in. So most of condensed matter, and pretty much all of the phases we knew about before 1980, we understand in terms of symmetry breaking. So for example, this is the lattice of a crystal. It can be perfect for about 1 million atoms in any direction. It has a lot of rotational and translational symmetries, but it has fewer than the vacuum, because now, for example, I have some discrete subgroup of rotations. And we can actually classify crystals by how did the symmetries break. And that turns out to be a very powerful way to classify ordered phases. The one that you might not think about much, but is actually most important for what comes later, is magnetism. So magnetism, not only do the electron spins pick out a direction in spin space, but they also break time reversal symmetry in the sense that the equations of motion can tell that there was a magnetic phase transition. There's now a difference between forward in time and backward in time. It was really understanding time reversal symmetry of fermions that led to some of these new developments in topological insulators. And just as proof that this isn't philosophy, or not pure philosophy, there is one very remarkable experimental prediction that comes out of symmetry breaking and is a nice example of how you can get universality even in messy macroscopic condensed matter systems. So if I look at the liquid-gas transition in water, at high enough pressure and temperature, so if I imagine a very good espresso machine, I might see that in fact that transition disappears. It disappears continuously as I approach that critical point. And this second order transition we can characterize by critical exponents, which as you know are scaling dimensions of fields in 5/4 theory. Now the remarkable fact from an experimental point of view is that the beta, the critical exponent that you measure here, as the density difference between liquid and gas near the critical point is exactly the same as the magnetization, or the difference between upspins and downspins states, in something like a bar of iron near the temperature where the magnetism disappears, the so-called Curie temperature. So that's one kind of universality. It was really only understood in the 70s. What about other kinds? So essentially, by serendipity, Klaus von Klitzing and collaborators were doing measurements on two-dimensional electron gases, and they found something remarkable. So for use in your cell phone and other practical devices, it's nice to make two-dimensional electron gases, which just means that one is in the lowest quantum state in the vertical direction. We're at low temperature compared to the splitting, so we just ignore all excitations in the z direction. If you put on a magnetic field, run a current along x, measure the voltage along y, which is so-called Hall effect measurement. This is a very standard semiconductor measurement to figure out how many carriers are there, and are they electrons or holes. Well, you see surprising plateaus, and they're flat to about 1 part in a billion. And on one of these plateaus, and I will talk about more complicated plateaus later, but in the original samples, one sees a conductance or conductivity. In 2D, those have the same units and geometrical properties in the Hall direction, of an integer times e squared over h. So what's a bit remarkable, this is just bare electron charge and Planck's constant. This is a big material with plenty of interactions, plenty of defects, plenty of thermal fluctuations, and somehow none of those matter. So that's pretty remarkable precision. And actually, I realize that for most of the people in this room, E is 1 and H bar is 1. So this looks like you've just managed to measure some 1 over 2 pi or something. But it turns out that this number, even though E is small and H is small, this is a very human scale number. The inverse of this is about 26 kiloohms. If you've ever measured the resistance of your body by accident, it's about 5 kiloohms. So it's a very human kind of scale. So two definitions to start with, and we'll use a more sophisticated definition in lecture 2, are that where that quantization comes from is topological order instead of symmetry breaking order. And there are plenty of phases that combine both of those ideas, like topological superconductors. But something I can measure in a topological ordered phase is given by a topological invariant. And I think you all know here what a topological invariant is. I'll just explain the particular kind that come up in solids. And then a more practical definition, which is often how these things are measured, is that most of the topological phases that we know about, and I think almost certainly the ones that we have very good experimental evidence for, are gapped and more or less inert at low energy in the bulk. But whenever I put them next to a ordinary insulator or vacuum or something like that, there's a gapless metallic edge or surface state. So I want to sort of give rough pictures for how these are connected, and then better pictures later on. The traditional picture of the Hall effect would be something like the following. That let me just think about two-dimensional electrons in a magnetic field. So if I ask, well, how could I have guessed that this conductivity is special? Well, the classical Hall measurement, I won't derive this, it's just simple, you can do it with semi-classical physics. You get that the Hall conductivity is proportional to the number and the sign of the charge carriers. If I plug in that measurement, what I get is that there are certain preferred densities of electrons, which is strange because in reality the density is not really precisely fixed, or we can change it. But we sort of knew that this was a special density. It's the density of filled Landau levels, and I'll draw a picture for that in a second. But basically, what I mean by that is, if I quantize the electronic states in constant magnetic field, I get harmonic oscillator levels. They're just evenly spaced in energy. And the density of states in a level is exactly this areal density, where L is the so-called magnetic length. So you could say that the only surprise in the integer quantum Hall effect is just how precise the quantization is. That's the sort of topological aspect. In fact, people sort of thought before that there might be features or oscillations or something, but before the experiment, no one knew how precise it would be. So here is maybe where I should do a little bit on the blackboard to explain where the topology comes in and give Laughlin's original argument. And then we will give a more sophisticated version of the argument by Thouless et al. That more or less languished for about 20 or 25 years before topological insulators came along and we needed it. So, okay, the idea of the Landau levels, if I had a perfectly clean system with a magnetic field, say, into the board, my states would be some highly degenerate sets where these energies, for example, this one is h bar omega c by 2, this is 3 h bar omega c by 2. So if I were going to draw, let's say, the density of states, it would be a set of delta functions. So what happens in a real system, at least at the single electron level, we know pretty well. If I just looked at the density of states, I would see little peaks, but nothing very dramatic. But what is dramatic is where are the states localized and where are they extended? So localized means that the electron wave function falls off exponentially fast away from some region. That is not true, or to be precise, I can choose extended combinations of the Landau level states. What happens, instead of looking at the density of the states, I should look at what we call the localization length. The localization length in general is finite, but it has divergences at some critical energies. For weak enough disorder, these are just the Landau level energies. And let me call this exponent mu. So that's to say that if I were to instead plot the localization length, it would have some divergences. And those are where I have transitions between quantum Hall states, and let me now justify that statement. But as an example of how there are many things we don't know, we thought we knew this exponent numerically and not theoretically. And when I mean not theoretically, we don't actually even have a controlled expansion for this in the non-interacting limit. It's a notoriously hard problem. It turns out even the numerics have slightly evolved. This number used to be about 2.3, now it's about 2.5, but we don't quite know in some sense why it's 2.5 yet. But let's forget about that and figure out why is there a quantum Hall effect. If I believe in that picture of the electronic states, why should I see this remarkable quantization? So the picture that Laughlin had was basically, let me think about a ring geometry. So this annulus, this is my possibly integer quantum Hall state. And what I want to think about is creating an electric field going that way by adiabatically ramping a flux through the center of the ring. So I've got some time-dependent flux that I slowly increase from 0 to the single electron flux quantum adiabatically. And the point of that flux is that we know that that flux can be gauged away, and I'm making the assumption that this is inside a solenoid or something, so magnetic field does not penetrate to the sample, which means one flux quantum, the eigenstates with one flux quantum are gauge equivalent to the eigenstates with no flux quanta. So what could have happened in the process of doing this adiabatically? Well, first of all, in order to be able to do it adiabatically, for that to have a meaning, I should either have an energy gap above the ground state or what we call a mobility gap. Mobility gap means a gap to extended states. If all my states are localized, they're not going to matter for this argument. What really matters are the extended states. So Laughlin's argument was that, okay, I've gone through some adiabatic process. I have the same eigenstates at the end of the process. So the eigenstates are kind of continuously evolving. In fact, the way to picture this is that the eigenstates are like a conveyor belt that's kind of moving outward and shuttling charge. Because what must have happened the argument was that an integer number of charges and electrons have moved across the ring. The idea being that there's no way, if I've always got this gap, and if my states are back to what they were before, that I could have left behind some fraction of an electron sitting in the middle. Although, as you may know, there is something called the fractional quantum Hall effect, where in fact the assumptions of this argument do not hold. So be forewarned that this is not a perfect argument, but it is correct for integer quantum Hall states. So the picture also implies something very subtle, which was pointed out by Halperin, really, which is that, okay, so I should think about where the electrons are coming from. What this should mean is that there's a reservoir of electrons that they can move into or come out of adiabatically at the boundaries of my disk, and these are the so-called edge states. And for that to work adiabatically, these must be gapless. So finally, as a little exercise, if you use the Maxwell equation relating the curl of E to dB by dt and figure out, okay, well, as I did the ramping up of one flux quantum, if I had an integer number of electrons move, then that is indeed exactly sigma xy is n e squared over h. The c in my units was in the Maxwell equation, so that's where I lose the c, and then e over h here and e there. So that's the Laughlin argument, but it leaves a few things unanswered, like how could I understand these edge states more abstractly, and that we will talk about when we come to the Chern-Simons picture of the Hall effect. Let me actually, while I'm on the board, do one other little exercise that at first glance is unrelated, but we're going to give a better picture of the topology here, make it more explicit. But as a warm-up for that, so I'm basically going to discuss topology of wave functions, or cohomology invariance. But to give a quick picture of another integer, let me think about topology of Hamiltonians. And in particular, without explaining why I want to think about this, let me think about maps from the two-sphere to non-degenerate two-by-two Hamiltonians. And the reason for doing this, the topological invariant that kind of underlies the Laughlin argument is some integer valued thing, and there are at least two different useful pictures for it. One I have in the slides. Let me give another one, if you like homotopy. So,
very sorry to be so stupid, but I didn't get your argument here. Was there a B field inside your ring or not?
There's a B field in the center, and that's creating an electric field.
Yes,
here.
but there's no B field.
I said the B field does not penetrate the ring. That's right.
So then, what does I thought this quantum Hall effect had to do with the B field being in your sample?
It does. So you can say, how does this have to do with the sample? Well, it's pretty subtle. So the idea is that where the conduction actually occurs in a typical experiment is not by this process, but by a different process. And let me try to sketch how the two are related. So here, I'm actually changing the Hilbert space, but not applying a magnetic field. So as I change the flux, the states are evolving, which is not our normal picture of transport. Normally, we think of solids as having fixed energy levels, and we just change their occupancies. So what actually goes on in the Hall measurement really has nothing to do with this, because here, there's no edge connecting the inside to the outside, but the transport is nevertheless happening through the bulk because the eigenstates are moving over. In a normal quantum Hall measurement, I would have say a Hall bar geometry. So let's say I've got, okay, I can do either 2-terminal or 4-terminal measurements, but let's say I've got V1 and V2. The picture of where the conduction happens, let me do a 2-terminal measurement for simplicity, is it actually has nothing to do with the bulk, and it's entirely on the edge. And what's happening is that each edge is a chiral fermion. So what happens is, by chiral, I mean that the fermions on the top move that way, the fermions on the bottom move that way. And a perfect one-dimensional conductor, and these actually have to be perfect because there's nothing for them to backscatter into, has 2-terminal conductance of e squared over h, although that was only directly observed in 1988, which is 8 years after the quantum Hall effect. So basically, this will give me a 2-terminal conductance of e squared over h, where if V1 is greater than V2, you could view that as coming from this edge, and if V2 is greater than 1, you could view it as coming from that edge if you want to use electrons rather than holes. So it's a bit strange, and this is kind of what Halperin explained, that the actual transport in an experiment is more in a limit where the states are fixed, and what I'm doing is just changing the population of the states, while Laughlin's argument for the precision of quantization, the edge only appears as a reservoir. There's no transport along the edge. But we will see that the bulk and the edge are kind of intimately connected at increasing levels of sophistication. Yeah.
How do impurities enter the picture?
Let me come to that later. I will. And interactions and other things. But it's good to start simple. OK. Oh, yes, the homotopy thing. So yeah, the idea was going to be, well, how, OK, if we were just interested in topology and condensed matter, quantum condensed matter, well, the simplest problem we might try to solve would be something like this. So if I have 2 by 2 Hamiltonians, well, non-degenerate 2 by 2 Hamiltonians I could write as and the non-degeneracy condition is just that A2, A3, and A4 are not all 0 at the same time. So if that's true, well, this is just an overall shift of the energy. It's not going to do anything interesting topologically, so let me forget about that. Well, this is punctured R3. That is, the space of 2 by 2 non-degenerate Hamiltonians, I'm arguing if I can forget about that, is like 3 space, but I don't allow the origin. And that, for our purposes, in particular for computing winding numbers and things like that, is basically like S2. So this is intuitively, removing the origin lets me pull out all the points near the origin to the unit sphere along their radius. All the points from outside I can pull in along their radius. So for the purpose of computing winding numbers, that's going to be the same as S2. And then maps from S2 to S2, which we write as pi2 of S2. So pi n in general is maps from Sn to something. This is equal to the integers. Basically, pi n of Sn is z. For a circle, that's saying if you wrap around a circle, you can wrap an integer number of times, and then an intuitive generalization of that is that I can wrap one sphere around another an integer number of times. So for example, if I put a balloon around my basketball, there is no way to get the balloon off the basketball without cutting the balloon, and so on. So this integer, this is maybe the simplest picture I know for actually that integer. So now I have to explain how those are connected and how that appears in a physical situation. So what I'm instead going to do is talk a little bit about cohomology first, but it will, I promise, be the same invariant. So to give some idea, think about just the Gauss-Bonnet formula, which is the following. If I think about 2-dimensional surfaces in 3 space, I can define 2 radii of curvature in perpendicular directions at any point. And I want to define that with a sign so that the sphere has positive curvature, both curvatures have the same sense, and the equator of the hyperboloid has negative curvature, one is toward me and one is away. And then, you know, the magic is that when I integrate a curvature over a closed surface, I occasionally get something that's a nice topological invariant. So for this case, I get 2 pi times the Euler characteristic, basically the number of holes. So for example, the sphere, this has surface area 4 pi r squared. Gaussian curvature is 1 over r squared, so I get 4 pi. And it's 4 pi however I distort the sphere, as long as I don't cut it. The torus will give me 0 because the negative curvature on the inside cancels out the positive curvature on the outside. That's why we can faithfully represent the torus as like a square with periodic boundary conditions. So the way I'm now going to explain the Hall effect is due to Thales et al., as I mentioned. And it's basically to think about a similar kind of invariant, integrating a curvature over a surface. So what's the curvature and what's the surface? Well, you need to know one fact about solids. And it's a fact that we, even in condensed matter, often ignore. If I think about electronic wave functions in a crystal, and this will generalize very simply to disorder by the end of this talk. Let me just think about a crystal and think about single electron wave functions. then they look like plane waves times a periodic part. So the periodic part, I mean periodic with the same periodicity as the unit cell. And that periodic part, we don't normally worry about it too much. Like, for example, if you see an energy band structure, that's a plot of energy versus K. K is so-called crystal momentum. It turns out that all the topological insulators, quantum Hall effect, anomalous Hall effect, various other things, those all are coming from this other part, which is sort of the actual wave function in the unit cell. One little note about K, we call it crystal momentum. It's only well defined up to the reciprocal lattice of my original lattice in real space. We call a fundamental cell of the reciprocal lattice the Brillouin zone. So for our purposes, just think of that as a d-dimensional torus for a d-dimensional crystal. So that d-dimensional torus is going to be our surface. It's basically just the set of inequivalent crystal momenta. So we're now going to define a gauge field on that surface. And the surprise, which we keep finding examples of, is that all the natural objects from a gauge field that you learn about in field theory and particle physics have some physical meaning when you apply them to the gauge fields in crystals. Although it took a long time to realize that somehow. So Dallas's paper was actually even before Berry's seminal paper, but let me explain the curvature in terms of Berry phases. So the adiabatic theorem in quantum mechanics, you all know, if I start in a non-degenerate state and change the Hamiltonian slowly, I stay there. So an abelian Berry phase is basically the statement that not only do I stay in the same state to exponentially good accuracy, but if I move around a closed path and bring the Hamiltonian back to where I started in parameter space, I generate a phase. So that phase, and here I'm kind of expressing it in terms of time, but at least as a mathematical object, any path in parameter space I can associate with the phase if it's a closed path. And the way I compute the phase is by integrating what looks like a vector potential. And that vector potential comes from how do the wave functions evolve as a function of the parameter. So you might immediately say, well, what if I choose one definition of the wave function and you choose a different one? If I've only got one non-degenerate state, that's basically just choosing a different phase. But eventually we'll be talking about n-fold degeneracies where we're talking about a UN matrix. So there is a kind of, if you like, gauge freedom here, and that's a hint for why gauge fields are important. So the nice thing about writing it as an integral of a vector potential is that if I choose psi and you choose a different phase, let me assume at least that we differ by some smooth function, then the vector potential just changes by a gradient. So that tells us how could we make possibly physical things out of A. We might make loop integrals, or even simpler, we could just take the curl of A, which I'm going to call the Berry curvature. Basically, if I treated A like an abelian electrodynamic vector potential, this is just the field strength tensor. So that might be physical, and in fact it is. It turns out that if I integrate that over the two-dimensional Brillouin zone, which is just a square with periodic boundary conditions, I get the following. Every band, so this is just writing out integral of f in terms of the u in the underlying wave function. Every band contributes an integer. The integral, this is very much like the Gauss-Bonnet formula. The integral of this first Chern form, which is the formal name for the Berry curvature, when I integrate that over a closed two-manifold, in this case just two-dimensional torus, I get an integer. So this is kind of the mathematics. And then the physics is that for every band, the integer just tells me how much does that band, if it's full, contribute to the quantum Hall effect. So that integer, if I wanted to understand it differently, well here, in a way, this looks a bit messy because I had to define something which is gauge dependent, which is the wave function, in order to compute something which is physical and hence gauge invariant, which is the quantum Hall effect. If I wanted to do it slightly more mathematically simply, what I could instead do is instead of looking at the wave function, look at the Hamiltonian of which that wave function is an eigenstate. Then the generalization of this, well, so first of all, you can kind of convince yourself intuitively that maps from T2 to S2 are also classified by an integer. So this is S2 to S2. T2 is what I should really think about for the Brillouin zone, but T2 is in a sense like a sphere plus a couple of non-contractible circles. The circles, when I look at their image on the sphere, can be shrunk to a point. So this is also classified by Z. And if I went from 2 bands to n bands, I would find that there are n minus 1 free integers. In this simple 2-band case, there's just 1 free integer. In general, there are Chern numbers for every band, but they have to sum to 0 because the sum of all the bands is a trivial bundle. So that is sort of the beginning of a more topological picture. And if you're wondering, well, how did they derive this? They actually thought, let's try not to be as clever as Laughlin. So this argument certainly has some subtleties. What they said was, well, let's just sit down and compute the Kubo formula, which is basically just our fundamental definition of a conductivity. So suppose you didn't know any better, and you tried to compute the Kubo formula of electrons in a lattice in a magnetic field. With a bit of massaging, they were able to get this expression. So that's a bit surprising, because normally there are energy denominators. It's basically a perturbation theory calculation. But the trick is, with enough work, and I won't do it because it's just kind of tedious, you wind up with what we call a pure Berry phase. There are no energy denominators. Everything in this expression is just a geometrical property of the wave functions. It doesn't care about the gap or anything like that. Now, one question you might have, well, for this to work, all my bands need to be completely filled or completely empty, which is what we call a band insulator. There are no partially filled bands at the Fermi level, which is what we call a metal. So how does this actually conduct charge? And that is the idea of these edge states, that what the topological invariant really means in physical terms, and we're going to give an argument for this in Chern-Simons theory in the second lecture based on work of Witten, Wen, and others. What the topological invariant tells me is if I put a boundary on the theory, so if I've got my quantum Hall effect with, say, this integer n equal to 1, the integer n tells me how many perfect quantum wires do there have to be at the boundary. And a little calculation, basically just filling electron states up to the chemical potential, you can compute that a perfect wire gives you a conductance of E squared over H. So that's sort of more important in experiment, actually, than the Laughlin geometry. Yes?
Why is the sum of all the bands a trivial bundle, and why is it important again? Can you say that again?
It's not very important in practice. The reason why it's true is the way to think about what happens as I change momentum. Let's think about, I guess, this is some finite dimensional quantum mechanics problem. The Hamiltonian is changing, but the total Hilbert space is not evolving. If I take all the bands together, that's kind of the total Hilbert space, and that is more or less constant with K. So that's mathematically how the sum comes out to be, but we're never going to use that. Yeah, but if you like, in this example, mapping the sphere to the sphere, there's only one integer, they're not two integers. So that's, in that case, you can see that if I tried to compute the Chern number of the lower band in this example, I would get plus n. The Chern number of the other band would give me minus n. So they do indeed sum to 0. In this case, there's just one Chern number. In practice, the reason why this is not that important physically, we normally figure that energy is bounded below but not above. So really, this is infinite dimensional. It's just harder to draw a picture in infinite dimensions. So I figured I'd do the sphere.
Sean, I think I'm missing something basic. So here you compute these integers by thinking about band structure, but there's no mention of magnetic fields.
Well, the magnetic field came in the wave functions, but that's true. It's not very explicit here. That is to say, for this to work, the technical assumption I need to make is that I put on a magnetic field that is commensurate with the lattice, in the sense that I had a rational number of flux quanta in the original unit cell of the lattice, which means I can define a supercell. Like if I had P over Q flux quanta per unit cell, I now define a supercell of Q original unit cells. Then I can apply Bloch's theorem because I have periodicity. So really, you're right that the magnetic field doesn't appear explicitly, it just appears in U. If I had time reversal symmetry, it turns out that every one of these integers is 0, which makes sense because this effect breaks time reversal. So that is actually leaping ahead. In fact, it's good because it's the next slide or two. Where things were stuck, if you like, for about 20 years was most solids don't have broken time reversal. They're mostly non-magnetic. And to actually push a solid magnetic enough to have this effect by applying a magnetic field is very hard. You're sort of limited to low temperatures, strong magnetic fields, etc. But There are plenty of forces that are intrinsic in solids. In particular, spin-orbit coupling is there in every solid. Could I have a topological invariant generated by spin-orbit coupling? And that is what happens in these topological insulators. Maybe one last slide just to try to draw a picture, more or less, and this is not a great picture. We'll give a better one in a second, or a bit later. We'll give the Chern-Simons picture later on. But here's a very rough kind of proof by contradiction, at least for a smooth boundary, of why a topological invariant might be associated with a metallic edge. So let's assume that given a band insulator, so if all bands are empty or occupied, I can define, or empty or fully occupied, I can define this integer, and therefore it can't vary if the system remains insulating. Well, basically, that means the electron wave functions inside the quantum Hall region are topologically non-trivial, like this knot. Outside, they're topologically trivial. So in between, at least if I could go smoothly enough that band structure is a well-defined concept, in between I must have violated the assumption that the system was insulating, and that's my metal. That's like cutting the string. Basically, the system has to go metallic so that the topological invariant is not well defined. Now, you might ask, what about a sharp edge? Because then I don't have this smoothness. What we're going to argue later on is that if I write down the right field theory for the bulk, it actually is anomalous. It doesn't have gauge invariance unless I add something at the boundary, and that's why there has to be some gapless dynamical degree of freedom at the boundary, whatever the boundary is. But we'll come to that. So now we get to what's kind of a surprise, even though this is still more or less single electron physics. The new phases we can understand in the same way starting from band structure. So we can compute topological invariants. They're just slightly more complicated, but they still have pretty simple physical pictures. And they're going to result from spin-orbit coupling. And one nice thing about spin-orbit coupling is now I don't have to make this assumption about commensurability of the magnetic field. I can just say there is a crystal lattice. Whatever the spin-orbit coupling is, it has the periodicity of the lattice. So this is, David's point, that the magnetic field only came in through the block wave function. So I could take what I had before and just apply it to any crystal. The problem is that the invariance we had before will all turn out to be zero. So the physical origin is going to be spin-orbit coupling. One exciting thing is that the quantum Hall effect is just a two-dimensional phenomenon, while these new states occur in both 2D and 3D. And actually, I'm going to focus on the 3D one, because that's a bit more exciting and more connected to particle physics in some ways. And finally, the way that these were seen experimentally is a little bit different. So here is the basic idea, although no one believed it, and for good reason, until 2005. Think about spin-orbit coupling. So just think about L dot S from your undergrad quantum mechanics, where L is the orbital angular momentum and S is the spin. So this means that if I fix the spin up, I have a momentum-dependent force, which is like a magnetic field. But the effective magnetic field is opposite for spin-up electrons and spin-down electrons. But at least I could cook up a toy model where, say, spin along some axis is a good quantum number. Let's call that Z. Spin-up electrons are in a quantum Hall state with edge mode going one way, and spin-down electrons are in a quantum Hall state with the edge mode going the other way. So this was written down at the toy model level for some time, and a good example is 2004. But the reason why people were skeptical, it wasn't really understood how this could be stable, because we didn't have any idea of a topological invariant. It looks basically like a one-dimensional wire. And some of you may know that one-dimensional wires are tremendously unstable to disorder in general if I have modes going in both directions. The quantum Hall effect gets around that because if there's only one direction of mode, there's nothing really for it to backscatter to. Normally with two modes, if I turn on disorder, we might have expected them to go away. It turns out that people sort of knew there could be exceptions to that if you look carefully enough in the literature, but they weren't really thinking about it in this topological phase context. So this was called the quantum spin Hall effect originally. You can write something like a conserved spin current, but that's not really well defined, so I won't say much more about it. But basically, this would just be two copies of the quantum Hall effect in opposite directions. In real solids, there's no magic z-axis where upspin and downspin electrons decouple. So what happens in a real system? We thought that up and down would mix, there would be backscattering, the edge would disappear. And then Kane and Mealy showed that that's not quite right. What they showed basically is that there's a new kind of topological invariant in 2 dimensions if I have time reversal invariant systems of fermions. And it doesn't take integer values, it just takes 2 possible values, even or odd. In hindsight, we now call the even case ordinary insulator and the topological case the 2D topological insulator. So I want to give a quick sketch of where this odd-even effect comes from, and then turns out the Berry phase expression, one way to justify that is actually like Wess-Zumino terms in field theory. So here is the, very quickly, this is a model that was written down. I think I will skip over this in the interest of time, but if anyone wants an explicit lattice model that realizes this topological insulator, that's actually what Kane and Milley did. They basically took nearest neighbor hopping on the honeycomb lattice, which is famous because it's the graphene Hamiltonian to a very good approximation, and this has Dirac nodes. It's what we call a semimetal. The Fermi surface is 2 points, or if I include spin, 4 points. And that means it might be possible to open up a gap with various perturbations. So an ordinary insulator, one way to open up a gap in graphene would be if the 2 sublattices, like the left site and the right site of a horizontal bond, had different potentials, so-called staggered potentials independent of spin, open up a gap and give me a very boring insulator. But if I start to think about spin-dependent terms, then I get something interesting. And the way they stumbled on their result was nice. They took 2 copies of a famous model introduced by Haldane in 1988, basically 2 copies where, note that SZ appears here, which means that it's like a magnetic field one way for spin up and one way for spin down. So this made 2 copies of the quantum Hall effect. And then they started playing around with what if we try to make it more realistic by adding some spin orbit term that has all directions of the spin, which means it mixes up and down. So they sort of did some numerics on lattice models, which is easy because they're not interacting here, and noticed that there was a very stable edge mode, and then started asking why. So just to connect this to what I said before, if I had a good quantum number like SZ, which means I can divide my electrons into upspin electrons and downspin electrons and they don't mix at all, the total Chern number is 0, but I could define something like a spin Chern number that would be well defined. But in general, this does not exist. There is no such integer. There is only a Z2. And why there is a Z2 is what I now want to explain. But once you accept that there are topological invariants that are not integers, everything is very similar to what we did before with the quantum Hall effect. So here is why fermions are special in a way that they're not for the quantum Hall effect, actually. So time reversal symmetry for spin half particles implies extra degeneracies. Basically, time reversal symmetry means that any state is degenerate with its time reversal conjugate. For bosons, a state can be its own time reversal conjugate, but that never happens for fermions, or spin half particles, as explained by Kramers a long time ago in the early days of quantum mechanics. Now, what that means for us, this is a plot of energy on the vertical axis versus momentum in the horizontal axis. So this is a one-dimensional dispersion for the edge mode. Let me imagine upspin going right and downspin going left. They might not be perfect spin eigenstates. What I care about is that what's moving right is the time reversal conjugate of what's moving left, and I have time reversal invariance in the system. Well, solid circle means I've put an electron in the state, and empty circle means I haven't. Then the only low energy backscattering process would be I bounce off some impurities, say, and I go from here to there. But if you remember this Kramers pair idea, that's not allowed in a time reversal symmetric system because that would be mixing the 2 states of a Kramers pair, which could split the pair in energy. So this is forbidden. If you like, a way to think about it is that this is half of a quantum wire. A normal quantum wire would have up and down going one way, up and down going the other way. And that is unstable because I can scatter from the right mover to the left mover that is not its time reversal conjugate. Is that making sense? Or? Okay. So like if I took a carbon nanotube or something, then upspin to downspin is forbidden. Those 2 are time reversal conjugates, but up to up is allowed, down to down is allowed. This winds up being localized, but somehow half of a quantum wire is much more stable than a quantum wire. Or in general, an odd number is stable. We believe that if I start with an odd number, they will localize in pairs until I'm left with 1 going each way. And an even number will localize in pairs until I get to 0. But note that this is different from the quantum Hall effect in that we needed a symmetry. So this is kind of a topological phase or topological invariant that's defined only if I have time reversal symmetry. If I break time reversal, then even this can localize, or gap. So if you're interested in, it'd be more elegant not to just have some picture for why the edge is stable. I ought to be able to say, given the bulk, does this exist or not? And that sounds like a puzzle, because how can I have some bulk quantity that's a Z2? Well, here's the way it works. There are various ways to do it, but let me give my favorite. So if I take the Brillouin zone is a torus, so that's a nice closed manifold in 2D. If I cut it in half, which is kind of logical in a time reversal invariant system, because if I know what's going on at plus k, time reversal tells me what's going on at minus k. So let's take half the Brillouin zone. If I cut a donut in half, that has boundaries. Having boundaries is not good, because if I integrate the Chern number, and one comment is that because of those Kramer's degeneracies, bands naturally come in pairs. So now this is actually non-abelian, although it's only the trace that matters in this way of writing it. But this is not even an integer. This is an integral over an open manifold, or a manifold with boundary, so it'll just give me something messy. What I should think about doing is, how could I extend the space on which the problem is defined to make it a closed manifold, which basically amounts to, how can I put caps on my half donut to get a sphere, integrate over the sphere, and then it turns out I'll get the Chern number, which is an integer. But there's an ambiguity because I could have chosen different caps. And if this all sounds like a bizarre argument, you might recognize it's very similar to the way a Wess-Zumino term works. Namely, to define the Wess-Zumino term, we start off with a physical configuration space for the fields that's S2, like the surface of the sphere. But to write down the Wess-Zumino term, I extend that definition into the interior of the sphere. And the two things I have to show for that to work are that, first of all, I can always do that extension, which is a statement about the field configuration on the surface is contractible. And then I have to show that the physics is independent of which contraction I chose, which is a statement about a higher homotopy group, that basically the difference between contractions is classified by pi3, and that's an integer. So for us, we're doing the same thing. We have to show that contractions always exist, which is a statement about contractibility of Hamiltonians, the way we did it. And then we have to show that the contractions are unique, and the answer is they are not unique, but their parity is unique. So that's how, just given the bulk, I could actually compute something. And it turns out that, in a sense, some of these definitions are probably inferior to the axion electrodynamics definition in 3D that I'll give later on, but this was historically the sequence. And then finally,
this is for a two-dimensional.
So far, we're still in 2D. Yeah.
And this definition of Chern class for a manifold with boundary was known to mathematicians?
I don't think they put it in this form. It turns out that what had been studied well by mathematical physicists was not quite the right problem, because they had studied their definition of a time reversal invariant system, at least in some papers, was you're mapping K, like the Brillouin zone torus, to Hamiltonians that are time reversal invariant at every point. That isn't quite the way band structures work. It's what they call twisted K theory, where H of K is not itself time reversal invariant, but it's time reversal conjugate to H at minus K. So if K is equal to 0, or in general, if K is equal to minus K, those two definitions are the same, but they're actually different. And in particular, if you required that the time reversal, if you required the Hamiltonian be time reversal invariant at every K point independently, you get nothing in dimension less than 4. If you put in this twisting, then you get stuff in 2 and 3. And I will say, yeah, there are some, now a mathematical physicist named Kitaev and also a group in Santa Barbara, Andreas Ludwig and collaborators, have gone back and just revisited the question of, with this picture of time reversal and various symmetries, what are all the topological insulators and superconductors? And I'll flash up that table in the second lecture. So it has been done now, but it hadn't really been done before. At least, yeah. I don't think it was a surprise to mathematicians. I just don't think they were aware that it was a logical question to ask. That's probably the way to put it.
From what I understood, the time reversal invariance just allowed you to cut your Brillouin zone in half.
That's right, but for example, these points in the middle here are not time reversal invariant. It turns out that there are only 4 points where k is equal to minus k, which are the 4 points labeled here. So if I'd solved the problem in the other case, okay, so to be precise, where time reversal came in was in showing that the parity of this is well defined. And that is a subtlety where if I look at one of these caps, it turns out that this point is time reversal conjugate to itself, this is time reversal conjugate to itself. These lines connect points that are time reversal conjugate. That time reversal conjugacy condition is the essential part in the work of showing that two contractions differ only by an even integer. If I didn't have time reversal conjugacy, I would get that they differ by any integer, which means that the invariant is sort of vacuous. So time reversal does come in, but it's, the particular kind of time reversal that's right for solids is maybe not the simplest one that mathematicians have thought about. So I won't talk too much about experimental details, but if you're wondering how could this be seen, well, if I do this measurement now, so now I've got one right mover and one left mover at each edge, which means I get a factor of 2 here. And this is in zero magnetic field. So the theoretical prediction is that if I can make a two-dimensional sample that's in this state, normally a two-dimensional conductor, the conductance grows with the width. Here it doesn't. It basically conducts like a one-dimensional wire, even though it's a two-dimensional sample. And you can view that as half of a quantum wire wound up at the top edge and half of a quantum wire wound up at the down edge. And that was discovered experimentally in 2007. And it's took a while to be reproduced, but it has recently been by a group at Harvard as well. The original work was at Würzburg. But basically, it just looks like a decent plateau. Two-terminal measurements are never as precisely quantized. And in general, the corrections here are power law rather than exponentially small for reasons like inelastic scattering that I could go into if anyone's curious. But so it's never going to be 1 part in a billion, but there is a nice flat plateau where they're supposed to be. So that's 2D. I want to focus pretty much for the rest of what I say about topological insulators on 3D, because it's going to turn out that 3D teaches us something very basic about all solids, not just topological insulators, and it is a physical realization of axion electrodynamics. So if I try to make three-dimensional versions of the quantum Hall effect, what I find is that I can layer systems. So I could, for example, stack a bunch of quantum Hall planes in different directions, but there is nothing that's sort of isotropically 3D. I want to give a quick sketch based on what we know about time reversal and what we know about Z2 for why there is a topological invariant that's genuinely 3D in this Z2 type for time reversal invariant systems. And it's going to turn out to the fact that in time, it's the same thing as in time reversal invariant systems, the theta angle for electromagnetism is either 0 or pi. So I'm going to go pretty quickly through the band structure definition because it's now kind of obsolete, I suppose, but it was how we first figured these things out, I guess. The idea is the following. Time reversal, remembering that time reversal takes k to minus k, some planes are like two-dimensional time reversal invariant systems, and some are like 2D time reversal braking systems. So for example, think of the three-dimensional Brillouin zone, which is a torus with periodic boundary conditions. So kz equal to 0 gets taken to itself by time reversal. So I could label that by a 2D Z2 invariant. So does pi by a. Well, that gets taken to minus pi by a. I mean, that's the top surface, which is equivalent to the bottom. So I could also label that by a Z2 invariant. But the point is, in between, time reversal does not take, say, pi by 2a to itself. It takes it to somewhere down here. So what that means is that planes in between don't have a Z2 invariant. So I could go from ordinary here to topological there as two-dimensional problems, taking advantage of the fact that in between the invariant is not well defined, the 2D invariant. If I try to do that with a Hall effect, well, the Hall effect, that integer is defined for every one of these, which means it can't jump. So the way to make a strong topological insulator in 3D, which is the code name for the isotropic one, is to take a sequence of 2D problems that interpolates from, say, ordinary to topological, breaking time reversal in between, and not closing the gap, so remaining insulating. So there is some heavy work left that I'm not going to go through because this is the part that's obsolete to show that there is exactly one new invariant. That is, if I did this for z or for x or for y, if it was non-trivial for z, I would get the same answer for x and the same answer for y. That was the bulk of the paper, but now there's a much cleaner way to do this in terms of the Chern-Simons form of the Berry connection.
So can I ask one question? If you take a normal and a topological two-dimensional insulator and you put them together that way, you're guaranteed to get edge states. But you're saying you put them together that way, you can interpolate between them without closing the gap.
Yeah, so here this is just, that is true. And here, by interpolation, I guess I just mean changing parameters. But if I think about what that means in real space, then yes, you're right. That I could go smoothly from topological to ordinary by stacking, and it's only at the sides. While the 3D topological insulator at any surface will have a surface state. And that surface state is kind of neat. So until 2004, I guess, we didn't have any materials with effectively massless electrons. Well, we had massless quasi-particles in D-wave superconductors, of course. But then graphene came along, and then the surface state of the topological insulator has massless electrons. That is, there's a point Fermi surface, energy linear in K near it. For the simplest materials, there's exactly one of these. So in units where graphene has 4 Dirac fermions, the topological insulator surface has 1. And if you know about fermion doubling, we believe that a time reversal invariant 2D system has to have an even number of Dirac fermions. So if this only has 1, what's just like in the 2D case, I've basically taken a normal 2-dimensional time reversal invariant metal and kind of chopped it in half and put half at the top surface, half at the bottom surface. So we believe that this can only arise at the boundary if I have time reversal symmetry, and that's connected to why it's stable. So the other nice surprise is that you don't have to work very hard to make materials. So the 2-dimensional effect has only been, the samples have only been made by one group so far, but they've been distributed to other groups to measure. So I don't think there's any doubt about the result. While the 3D crystals that have this surface state are being worked on by of order 100 groups. And the way that they're measured is kind of simple. So if you remember what Einstein won his Nobel Prize for, it was largely the photoelectric effect, which is send in a photon, bounce out an electron. If you spend $1 billion or many billions of dollars and 100 years on doing this, you get pretty good at it. And that's what angle-resolved photoemission spectroscopy is. You just measure the electron more carefully, and you bounce it out with an X-ray. So if you do that, you basically have a very good measurement of band structure. And the only problem with photoemission is that you can't bounce out bulk electrons. You tend to dominantly bounce out surface electrons, so it's kind of surface sensitive, but that's good if you want surface states. So as an example of a topological insulator, Zahid Hassan and collaborators at Princeton and LBL were the first to do this type of experiment. Bismuth selenide is at least 50 years old. It's been known for ages to have a band gap between the filled states and the empty states of about 0.3 electron volt. If you do this photoemission measurement, you see that there are states in the band gap, and they even disperse like a Dirac cone. So this is energy versus momentum, and people can tell that these are actually localized at the surface. And the nice thing about this, just one comment on experiment, is the energy scale. Because, for example, this is a millikelvin experiment. Quantum Hall experiments in general are sort of 1 Kelvin scale, because one has to be below the cyclotron energy. In graphene, one can go a little bit higher. But here, 0.3 eV is way over 1,000 Kelvin. And this signature persists very clearly at 77 Kelvin, and to some extent even at room temperature. So all of a sudden, this is not low-dimensional physics. It's not 2D physics. It's all very common and easy to see.
What's the velocity?
It is of order 10 to the 5th meters per second. So it's slower than the speed of light, in case you were worried. Depends on the material. There's nothing quantized about that, but that's the order of magnitude. And yeah, I think I'll skip. So anyway, there are various other measurements and so on. But now one question that was already asked, I think now's a good time to answer. So far I've only been talking about non-interacting electrons and band structure. And that's not really satisfying because, first of all, we always have disorder. If it's really topological, it ought to be stable to disorder. And second, it's better to define a phase in terms of some physical response, the way that we define superconductivity in terms of the Meissner effect, which is kind of representation independent, I guess. It doesn't matter whether I'm thinking about it as single particles or not. So the integer quantum Hall effect, I want to sketch quickly how that is robust to both disorder interactions. It turns out that for topological insulators, robustness to disorder is easy. Robustness to interactions is hard and actually required kind of a new idea, or at least recognizing an old idea. So here's the way to kind of redefine, and this is just one line of algebra, but it requires a bit of thinking. It took Dallas et al. 3 years to realize that this same mathematical object, if you interpret it differently, is enough to prove that the quantum Hall effect is well defined with interactions and disorder. So what I want to do, this was the first Chern form of the non-interacting electron wave function. Phi is the many-body electron wave function. So that doesn't have this parameter momentum. I have to define some other parameter and then compute the Chern integral with respect to that. And the way that works is the following.
Sorry, what's
Yeah.
phi?
The phi is going to be the many-body wave function. So this was like one single electron state, and the many-body state would be some Slater determinant of those. So phi, I don't even, at this point, the reason for doing this is if I've got an interacting electron system, it's in general not some product of single particle wave functions. So I ought to be able to do it with the many particle wave function if I can. And the harder question are, what are these variables? Okay, so those are, you can think of them as either fluxes, magnetic fluxes, or boundary conditions. So the idea is I want to think about how does momentum actually show up in computing the Chern number. So if I think about a unit cell, well, when I hop to another unit cell, so I know that the UKs are eigenstates of some Hamiltonian. When I hop to a unit cell, I basically fold this back into my original one, but it picks up an extra phase factor, and that's where the momentum shows up, because the idea is that moving from one unit cell to the next, I don't just notice the periodic part, I notice the plane wave part as well. If I wanted to redefine what that means, I could think of the Brillouin zone. It's hard to draw it as a proper torus. So the Brillouin zone is a torus, and I'm going to define, in general, phases for the electrons that hop from one edge to the other. So let's call this one phi and this one theta. And if you're wondering, what does this physically mean? Well, this is just like I took my torus, I defined my quantum Hall system on a torus, and I put one magnetic flux, say phi, through one of the non-contractible circles and one through the other non-contractible circle. Then they again could do this Kubo formula calculation if you compute the conductivity now of the many-body problem, and argued that the conductivity is given by, if you like, an integral now over the response to boundary conditions, to these flux conditions of the many-body wave function. And the reason why that's nice is that this thing, now whatever my wave function is on the torus, I mean, there could be disorder, there could be interactions, it doesn't matter, this is still well defined even when the top definition is not. So basically by reinterpreting momentum as flux, and by going from single electron wave functions to many body wave functions, this works, but it doesn't work for the Z2 invariants. And if you're wondering why, well, for the Z2 invariant, it was crucial to have one fermion. If I have two fermions, I'm back to bosonic statistics, which means I no longer have Cramer's degeneracies and so on. So I won't try to convince you that it's impossible, but at least no one has figured out how to go from this to that in quite the same way once I've talking about interacting topological insulators. So yeah, this is kind of the statement that instead of defining things on half the Brillouin zone, I could now define things on half the flux torus for topological insulators. That works for disorder, because with disorder I still have single electron wave functions, but it doesn't work for interactions. So I think that is why one can argue for needing a better definition. I think I'll skip that. So now is maybe the time to and I somehow counted to 4, but there are only 3 lectures, I promise. So now is maybe the time to get to electrodynamics, axions, our first dose of field theory, because single electrons are great and all that, but I already argued it's not the be-all and end-all. We should have a definition that's more general. So just to quickly summarize, it turns out that in hindsight, the first topological insulator is the quasi-particles of one phase of superfluid helium-3. So when you normally hear about superfluid helium, that's helium-4, which is a boson. Helium-3 is a fermion. It forms atomic Cooper pairs. It's like an atomic neutral superconductor. And we believe, although they've never been seen, that that should have surface states that are kind of surface Majoranas. I'll say a little bit more about, so that's really a topological superconductor. I'll talk about those later on, but historically, the quasi-particle Hamiltonian in helium-3b is almost exactly the same as a simple model of a topological insulator Hamiltonian. That wasn't fully understood, but there are some partial understanding in the helium community. So, yeah.
Sorry, you said there was no argument that these edge states for topological insulators are stable against interactions, but there's evidence that it is.
No, there is an argument. I just haven't given it yet. So basically what I'm saying is if you try to imitate what you did for quantum Hall effect, that wouldn't get you very far. So I want to now give a better definition. But I'm going to focus on 3D, actually, because it turns out to be more natural in 3D. So let me say a little bit more about the Berry phase, because essentially the key is going to be that the non-abelian part of the Berry phase, which I haven't used so far, is the key to the three-dimensional topological insulator. So far I've been dealing, if you like, with trace of F, but the Chern-Simons form and second Chern form of F are kind of the right objects for topological insulators. But I wanted to flash this up to mention that, I'll be mentioning more open problems later on, but one is we don't really understand yet. We suspect that there are more physical consequences of these Berry gauge fields in solids, but the non-abelian parts have only been thought about for a few years, and we still just really have one or two examples for the non-abelian part. So if you have some knowledge of non-abelian gauge fields, you might think about what they could mean in solids if you want to, easy problem. So the point is going to be essentially to answer the following question. The Hall effect is quantized in the quantum Hall effect. I haven't yet answered the question of what's quantized in topological insulators. To be precise, in 2D I said this thing is quantized, but in 3D it isn't really obvious, and in fact there isn't, if I don't perturb the system, there isn't a quantized transport quantity. So what is quantized? I'm going to argue that there's a magnetoelectric effect that's quantized, and that's this axion electrodynamics. And it turns out that from that you learn about magnetoelectric effects in everything. And I think I'll be able to get started on this, but probably not finish in this lecture. So let me skip over some of the abelian Berry phase stuff. I'll come back to that later. So yeah, let me start with this. So we know that when we go into a solid, we can modify Maxwell's equations. We modify the dielectric constant, we modify the permeability. Maybe I induce the new terms as well. One of the most interesting would be a term like E dot B. So why don't I write E cross B or some rank 2 thing? Well, this one is special in that it's a total derivative. It's a total derivative of the electromagnetic Chern-Simons term, ADA, which is a clue that this might have something to do with boundaries or something topological. So E dot B is distinguished from the other magnetoelectric terms. Now, the normal picture, and in this next few slides, Roman letters mean electromagnetism, which for us is abelian. Script letters mean the Berry connection coming from the electrons in the solid, which for more than one band, and it turns out I need more than one band, that's non-abelian. To be precise, if I have n occupied bands, there's a UN bundle, which is the bundle of occupied wave functions. So E dot B, well, at first glance, this breaks time reversal because E is even under time reversal and B is odd. But there is a subtlety. I'm going to argue that theta is periodic with period 2 pi. I'm going to give a condensed matter picture for that. It's somewhat different from what's in this original Wilczek paper. Once I believe theta is periodic, then something special happens. Basically, if I think about time reversal, that takes theta to minus theta. Theta equal to 0 is fine. Theta equal to pi is also okay, because pi gets taken to minus pi. Once I believe in periodicity, I'm okay. So that says that if I have time reversal invariant insulators, and they should be 3D to have this effect, then there are two possible values of theta, which are 0 and pi. And it was pointed out by Chi, Hughes, and Zhang. It took a while, so this is the point, that 20 years is a long time, especially in California. My former boss, not anymore, but so 20 years was basically how long it took for people to realize that there are actually solids that realize the theta equal to pi state. Here's how that's connected to what I said before, and actually to a famous experiment on graphene. So the definition of the 3D topological insulator I gave before was that it's a material that has time reversal symmetry and has an odd number of Dirac fermions at the surface. So one special thing about an odd number of Dirac fermions, and we actually know this from graphene, or indirectly, is that if I apply a magnetic field, so if I try to put a system with an odd number of Dirac fermions into a quantum Hall state, I don't get an integer quantum Hall state, I get a half-integer quantum Hall state. I get 1/2, 3/2, whatever, times e squared over h, which corresponds to theta equal to pi in this expression. So in general, I don't know which half-integer I get. That depends on microscopic surface properties. But I get some half-integer here and some half-integer there. And if I believe in the surface Hall effect, well, then an electric field that I apply, say, generates circulating currents, which generates a magnetic moment, and that's just the physical content of this E dot B term. And in particular, E dot B and E cross B and so on, these have been measured in solids for many decades. They're called magnetoelectric effects, especially in multiferroic materials, because there are many solids whose crystal lattice breaks inversion and who have some form of magnetism or antiferromagnetism, which clearly allows this term. The special thing about time reversal is just that it quantizes theta. So the point is that in order to measure this, I would say it's not really defined if I don't perturb the surface, because then the surface is gapless. If I apply an electric field, I just get larger and larger charges building up at the boundary. It's a statement about what happens if I apply a surface perturbation that is small compared to the bulk gap. So this is actually using the fact that quantum Hall edge states are totally robust, while topological insulator surface states are only robust if I don't break time reversal. So that's saying if I apply a weak field, I generate a half-integer. I don't know which one, but half-integer just corresponds to theta E dot B with theta equal to pi. Jumping ahead a little bit.
Sorry, but B does break time reversal.
That's right. So in order to measure it, basically I broke time reversal by, yeah. It's a bit weird in that I'm assuming an order of limits where I weakly broke time reversal at the surface, but not strongly enough to perturb the bulk. If I applied a big magnetic field through the whole thing, then theta would no longer be quantized. But there's a limit where, let's say the bulk gap is 0.3 eV. Typical magnetic field Zeeman energy is like, 10 millielectron volts. So there's a pretty well-defined and experimentally realistic limit where applying a magnetic field is just a surface perturbation, and surface perturbations can't change theta. They can change the integer that appears in front, but basically theta is coming from the bulk. And just jumping ahead a bit, the reason why this makes sense, really theta E dot B is totally equivalent to surface quantum Hall effect, because the effective electromagnetic action for a quantum Hall state is ADA. We'll show that in the second lecture. That's saying that if I took a quantum Hall state and integrated out the electrons and asked, what does that generate for the electromagnetic field, I just get ADA, and the derivative of ADA is just E dot B. So if you like, whenever theta changes, I generate a quantum Hall layer. And I said that we kind of know that fact about Dirac fermions from graphene. What I mean is, if you measure the quantum Hall effect in graphene, well, that has 4 Dirac fermions. There are 2 inequivalent points in the Brillouin zone, and there are 2 spins. If I look at the integer quantum Hall measurement in graphene, which was one of the smoking guns for Dirac fermions, I don't see 0, 1, 2, 3 times e squared over h. I see -10, -6, -2, 2, 6, 10, which are 4 times the half integers. So that's how we kind of know experimentally even that 1 Dirac fermion equals a half integer quantum Hall effect, which corresponds through this one dimension, through this partial derivative, boundary effect to the E dot B term. So to kind of summarize this little bit, and then I'll, justify this starting in the next lecture. I think this is the last slide for right now. What I've said so far is that in insulators, topological insulators, have quantized theta, but in general, many insulators will have a theta, and I'm going to talk about it more generally. But for now, let's just say it's either 0 or pi. The way that's measured, once I've fixed my boundaries and gapped them so that theta is actually defined, well, then I can apply an electric field and measure a magnetic moment, or what's usually done is apply a magnetic field and measure electric polarization. So this means that there are actually two magnetic fields in the problem. There's one to gap the surfaces, and then there's another to generate the polarization, but you could just take one field and orient it properly. And then the part which is neat, that I'll get to in a second, is it gives a new definition of the topological invariant. Although in this case, it's just 0 or pi, so this kind of will leave us a nice open question for next time. So script A, that is the microscopic electron Berry connection. So now that's non-abelian, I said. If it's non-abelian, I'm not writing the band indices, but the upper indices would be which band I'm talking about. So in general, this is UN, n at least 2. So one natural object I can form from that is the so-called Chern-Simons form, which is this object in the trace. And that Chern-Simons form has an interesting property. So the abelian Chern-Simons form is totally gauge invariant, and I wouldn't need that part. The non-abelian one, you may know, has an interesting property, which is that under large gauge transformations, so this is now an integral over the 3D Brillouin zone, I can imagine making UN gauge transformations. There are non-contractible gauge transformations, what we call large gauge transformations. And if I do that, then this integral jumps. It jumps by a value corresponding to theta changing by 2 pi. So this is actually the mathematical statement of what it means to say that the bulk contribution is only well-defined modulo 2 pi. If I believe that the bulk contribution is the Chern-Simons integral of the Berry gauge field, then we know from the math of Chern-Simons that basically because pi 3 of U2 and higher is z, there's an ambiguity of 2 pi times an integer. So this is why, for example, this is what sort of quantizes the coefficient of Chern-Simons terms in field theory. So now the question that this raises, though, is that I could write this down for any insulator, including the 50 years worth of materials that have a magnetoelectric effect. So does the non-abelian gauge potential possibly have something to do with all insulators, not just topological insulators? The answer is yes. So that's one open thing for next time. But as I mentioned, there are probably other physical consequences of this gauge field that we don't know yet, aside from theta. And then a second question maybe for next time is, I said theta topological insulators induce a term that if you want, you could call a topological term that gets added to the electromagnetic action. But something I haven't said, and what I think is the main question for next time is, what is the universal description of topological phases in the sense that Ginzburg-Landau field theories are the universal description of symmetry breaking phases? So topological field theories are probably the right way to define topological phases, and that has some spectacular properties, especially in the fractional quantum Hall effect. So I think that's enough for now. Thank you.
Are there physical situations where you get bundles other than UN?
You can add additional symmetries. So I do have the table. Let's see. So yes is the short answer if you impose additional symmetry on the problem. So for example, time reversal gives this sort of, the conditions are not always easy. They're not always of the form that UN becomes some other Lie group. So time reversal, for example, gives this relation between what's going on at k and what's going on at minus k. But there are some cases where UN gets specialized to some other Lie group. And so, for example, topological superconductors are a case. Just jumping ahead a little bit, there's something that we call the tenfold way, which is a generalization of the threefold way of Wigner, which was unitary, symplectic, and orthogonal. If you add the possibility of superconductivity, you basically get sort of 10 symmetry classes, which are all distinguished effectively by what the bundle is. And in fact, what these mathematicians worked out that I mentioned, so in case you're wondering, 10 is obviously 3 times 3 plus 2 minus 1. So as we'll explain next time. But the point is that at least, yeah, we do understand some bundles, but I don't think not every. So I'd say not every Lie group would be realized, but at least 10 of them are.
Why would this Chern-Simons integral give 0 or pi? It seems like it could give anything at all.
Well, it's odd under time reversal. So it will give anything at all in other insulators. But if I have time reversal, the effect of time reversal is that theta goes to minus theta. So again, if I believe that theta is only well-defined modulo 2 pi, that means I have to get either 0 or pi.
What does time reversal do on your Berry connection?
Okay, so it flips K and it flips F, which is dA. But effectively, what it does on the Chern-Simons form, at least integrated over K, is it takes this to minus itself. That's the net effect. So and once I've got something that is odd and periodic, it has 2 values.
This might be my complete misunderstanding, but the Brilliant zone is in momentum space, correct?
Yes.
So you're integrating a Chern-Simons term over a momentum space. So I can't think of this connection as appearing in a covariant derivative.
You could. It's a derivative with respect to momentum. Yeah, but that's right. It is all in momentum space.
And so, and normally for U1 theory, there's no requirement, at least from a particle physics perspective, for periodicity of theta.
That's right. So the point is that this is from. So I didn't write the upper indices, but this is from the UN bundle of the bands. So the script A is not electromagnetism. So that's right. So for abelian, in fact. So that statement would mean that for one occupied band, this is gauge invariant, and that means it might actually be physical. And it is physical. It leads to something called a Hopf insulator, which is a bit esoteric, so I wasn't planning to say much about it. But if you want a little exercise, you learned the Hopf map in quantum mechanics probably without even knowing about it. It's how you get a normalized 2-component complex spinor to a real unit vector. That's a topologically non-trivial map from S3 to S2. If I took a 2-band band structure with one occupied band, if you like, and computed the abelian Chern-Simons form, that is now well-defined, as you say, and it actually turns out to be quantized for this particular case, and it computes the Hopf invariant. And that has some physical consequence, although it takes a lot of assumptions, so it's not, I wasn't going to say much.
But even if your Brilliant zone is compact, then even in the generic U1 case, you probably have quantization.
I think that's right. Yeah. So I think the only way to get U1 logically would be having just one occupied band. Yeah.
Even?
When you first learn about non-abelian Berry phases in terms of some adiabatic changing of the parameters in the Hamiltonian, and you start with one degenerate state and you rotate into one of the other states. Is there some physical way to think about that picture with Berry phases over momentum space?
Again, yeah, the only assumption is that things are smooth with respect to momentum. So it's an adiabatic evolution, if you like, through the Brillouin zone. It's not in the sense of time.
Physically, how does that happen? How do you?
Well, yeah, physically. Okay, so the way momentum shows up, if you think about the people who actually compute band structures, I mean, the momentum only comes in as a parameter. Like, let's say I've got, to take a simple model, there's something called a tight binding model, which would be, say, throw down n orbitals in the unit cell and basically put some hoppings between them and diagonalize an n by n matrix. So if you ask, well, what is the band structure of that? The way that momentum shows up is that when I hop from an orbital in one unit cell to the next, I project that back into my own unit cell, and the only way that the momentum shows up is as what is the phase factor I add or subtract, if I were going that way, whenever I have to get back to my unit cell from when I hop to. So I guess that's saying that all the physics should be continuous in that phase factor. But I don't have a more physical picture than that, I guess. Well, okay, there is one. Okay, yeah, give me one. We still have a couple minutes. So here's maybe the most physical picture of what A means. Although, yeah, I might say a bit more about this later. So let me make a slight abuse of math. Think about that. If I took the derivative, if I took this minus I dk of a plane wave, it would give me the R operator. In fact, that's true. What the Berry vector potential basically tells me is information about the position of the electron in the unit cell. And to make that very precise, electric polarization in solids is a quantity that goes back probably to antiquity and pyroelectricity and things like that. It was only realized around 1990 that polarization is a Berry case. It's basically just integral of A. That is, where the electron sits in the unit cell is something like integral of this thing, or average of R. So that's the most intuitive picture of A, but it's not that intuitive given that it took so long to figure out. I will say some consequences of this, but maybe one point to make is there's a big difference between odd and even dimensions. Basically, in odd dimensions, we naturally get quantities that are not quantized unless I add a symmetry. So polarization in general is not quantized, but if I added inversion symmetry, there are now 2 allowed polarizations. That theta angle in 3 spatial dimensions is not quantized until I add time reversal, and then I get 2 possibilities. While in even dimensions, I get these very robust things without symmetry, like the quantum Hall effect. And then, there's this table of everything in all dimensions that I'll save for next time. But more or less, A is, the adiabatic evolution is just how things change with momentum. The physical picture of what A is capturing is the location of the electron in the unit cell.
Okay, one more question maybe before we break.
I think that the quantum Hall effect with Hall conductivity quantized by half integer is special since the denominator is even. Is it the same with case of 3-dimensional topological insulator?
Well, here, if I took the 3-dimensional topological insulator, I'll always measure the 2 surfaces in parallel. So the total will turn out to be an integer. If I could measure one surface in isolation, I get a half integer. In general, to get an even denominator for the whole system requires strong interaction. So it can be done. It happens in the Bathian state in the quantum Hall effect, which is one of the fractional topological states that we'll talk about. But here, this half integer is just reflecting the fact that I took an ordinary metal, which would be an integer, and I just put one part at the top surface and one at the bottom surface. So it's not any fractional particle or anything. It's just spatially separating the 2 metals, is how I'd put it.
Okay, so we're breaking for lunch, but before we do, let's thank Joel again. Thank you.